All right, time to calibrate the screen here. And right here. Okay. Very good. All right. Moving on to 1.3. And I guess I'll have a sign-in sheet. There won't always be a sign-in sheet. I guess I could take your homework being the sign-in sheet, but we'll just have it like this. Does anybody have any homework to turn in? Huh? You do?
Tuesday?
A week ago. Wait a second. Yes, it is Tuesday. Yeah. So here's the thing. Sometimes people don't have homework, but they do show up to class. So that's, I guess, why we should send out the sign-in sheet. I should eventually start learning your names and just recognize your names so that I know, okay, so-and-so is here today. Yeah, thank you. I could take that. But until then, I'm just going to have to kind of resort to a sign-in sheet for now. Okay, let's get to 1.3. Coordinate plane. Okay, so we are now going to introduce the Cartesian coordinate system to our discussions. Okay, the Cartesian coordinate system is just the XY. And let's say you have two arbitrary vectors in the Cartesian coordinate plane, like so. And let's say we can call these rays, we can call them vectors. Really, they're just intersecting lines of some points. Let's say that C is equal to some 4, 1, and that B is equal to some 2, 4. Okay? We want to talk about our lines, our initial leg and our terminal leg, in something called standard position. Okay. So what does this mean? It means the terminal leg always lies on the positive x-axis. I mean the initial leg. The initial leg always lies on the positive x-axis. The initial Okay, so here's an example of standard position. You start out with the initial leg like this, and here's the terminal leg, and it goes through some angle theta. Initial, terminal. Okay. Something like this is clearly non-standard position. Okay, so we aspire to represent these situations in standard position. Okay. So let's talk about situation like so. Sometimes the terminal leg is referred to as the coincident leg. Sometimes it's referred to as the coincident leg. It's not like the coincidence in like the English language where you're like, oh, I too like coffee, what a coincidence. It's more like the incidence of an angle. It's a different usage of the word. It just means they both kind of meet at the same common point of the origin, if you will. Okay, so let's say we have some angle alpha here. Some point here on the coincident leg, P is equal to 3, 3. Okay, so it's a 3 here, 3 here. What if we want to find the coincident leg equation or the coincident line equation? How can we create an equation for a line? Meaning, let's not just have this like this. Let's extend this line out forever. Who here remembers the general equation of a line? Feel free to say it.
Y equals X.
Correct. That is a line, but it has slope 1 and y-intercept 0. So what is the most general equation for the line?
Y equals mx plus b.
Correct. That is the most general equation for a line. Y is equal to mx plus b. You, sir, were technically still correct because you set m equal to 1, b equal to 0. This is still a line, but this is only one special line, and this gives you every kind of line that there is, and there is an infinite number of them. So this is the general equation of a line. Okay. This means we can construct any line out of that equation, whereas y equals x is just one specific line. It's a line of slope 1 and y-intercept 0. How can we create a line for this incident ray? Incident leg, incident line. Well, we have to talk about the definition of slope. What did slope equal? Who could tell me from way back?
Rise over run.
Rise over run, but that's just verbally. What's it mathematically?
y2 minus y1 over x2 minus x1.
Yes, and this encodes the rise over run in it. Because y stands for vertical, and so change in y stands for whether you rise or whether you fall, and x stands for horizontal, and when you have changes in the horizontal, it's whether you run forward or backwards. That all depends on the sign on the m. Okay, but to do this, you need 2 points. You need some initial point, P1 equaling x1, y1. And you need some final point, x2 equaling y2. Notice here, we have to choose points on the line so that we can calculate the slope of the line. We already have 1 point on the line, this 3, 3. One advantageous point to pick is one at the origin, because it just makes the calculation so much easier. Okay, so then P1, if you will, is 0, 0, and P2, if you will, is 3, 3. So this equation just becomes 3 minus 0 divided by 3 minus 0. Aha, the slope is 1. Okay. Now, what is the y-intercept? B. But what is the y-intercept here? 0. So yeah, we are going to get this right here, right? Because we just visually see b is equal to 0, m is equal to 1, right? So y equals mx plus b becomes just y equals x because of this. And this transforms to that, y equals x. Very good. Okay. Now, let's do this again in a different situation. Let's do a situation like so. Let's create a standard position situation. So here's one initial leg. Here's a terminal leg. Here's some point on the terminal leg. And here's a rotation of some alpha. Okay. Let's say this point D is equal to -3, 4. How do we construct the line that would extend this terminal leg out?
First we need to find the slope,
Mm-hmm.
so we find another point,
What point would you like to use?
0, 0.
Yeah, the origin's a nice point. So the final, so we get y2 minus y1 over x2 minus x1. This is the same thing. It's 4 minus 0 divided by -3 minus 0. Which is -4/3 is our slope. What is the y-intercept?
0.
Yeah. If you're going to have this in standard form, the y-intercept must be 0 when it's in standard form. Okay? So our equation is going to be equal to y is equal to -4/3 x. Okay, moving on. Let's do a third example. We got it like this, we got it like this, some angle alpha. And let's say there's this point 2, 3 on it, this leg. Now, task 1. Find 2 points on the line other than the origin. Is it hot in here, yo? What is the thermostat up in here? Whew. Whew. I don't know why it's so
Does that
hot.
say 2, 3?
Yes, it does say 2, 3. I was looking for my water, but I didn't bring it to my office. I was going to pour some on my head. I wonder if the sink works. It worked back when I was a student here. Who here knows why we sweat? Why do human beings sweat?
Body's cooling down.
How does it cool the body down? On the molecular scale, what's going on? I totally just cannot teach until I cool off. I'm really hot right now. So the water molecules, are they at a higher energy state or lower energy state compared to gas molecules?
Higher.
Water is a higher energy state or lower energy state compared to gas?
Lower.
Lower, right? So it has to get some energy somewhere to turn into gas, right? Yeah. So when the water molecules evaporate off of your skin, they soak up that heat energy off of your skin to become gas. This is a process called evaporative cooling. And so if you're hot, just cover yourself up with some water or sweat or something, and it should cool you off because the body heat will warm up the liquid, converting it into a gas, and then it's going to steal that heat off of you and go out into the atmosphere. That's why we sweat. It's really cool. It's nice to have that sink here. Now I know I can always cool off if necessary. Okay. Now let's find some non-trivial points on this line. Right here. You guys are now all pretty good at creating a general equation for that line. So let me have it. What's the step-by-step process towards constructing an equation to that line? There we go. I don't want to hear what the line's equation is. I want to hear the step-by-step process towards attaining the equation. Find the slope. So how do I find the slope? If I can't pick the origin, what could I pick?
You could pick 3, 0.
Yeah,
Equals 3.
I'm forcing you to estimate, aren't I? So let me put some hash marks here.
What do you?
Right?
2, 0.
So yeah, like right here, that would be like at 1, 1/2. This is clearly at like 2, 3, right? So 1, 1/2 works, right? 1, I don't mean 1, 1/2. I mean 1 and 1.5 here. Maybe that's why some of you look perplexed. 1.5, right? If this is 1 and this is 2, right in between them is 1.5, right? Okay, so another non-trivial point that isn't on the origin here would be, let's say 1.5. So we can find the slope. The final y being 3 minus initial y being 1.5, all over final x being 2 minus initial x being 1. What does the top give us?
1.5.
1.5 divided by 1 is what? It's a 1.5, and this is our slope. And fraction notation, we have 3/2, right? This is our m. So y is going to equal to 3/2 x. We could have constructed that info with using the origin though still, so. Okay. Now, what if I wanted to find any point on this line? What if I wanted to see what is this at -40? What is the y value here at -40? Here's a hint. This equation for a line y is a function of x. What does it mean to be a function of x? If y is a function of x, that means y's values are determined by the input values x. So y is dependent on what we put into it. Okay. What am I going to put into x if I want to know what y is at -40? what would I put for negative 40? Where in the equation would I replace? We would wish to evaluate what is y of negative 40, meaning we just replace the x with a negative 40 and see what the y becomes in the equation. Okay? We give it the input negative 40 and calculate what the output is. So the number it spits out will be what it is over here. And that makes sense because it's going to be a negative number. And that makes sense because this is a negative on the y-axis. Okay? So let's do the computation. This then becomes 3 times a negative 20. Right? So at negative 40, this line that is discovered is at negative 60. You guys see what I'm talking about now? Aha. So this point that we're talking about here is negative 40, comma, negative 60. So you'll be using this in your homework for this section. This idea that, hey, I can find any point on the line. I just find the equation of the line, pick an x that I want it to be at, find where the corresponding y should be according to the equation. Now, given this same line here, okay, let's talk about some other stuff. Let's compare the ratio of x over y to y over x for various points on the line. So, for instance, if we're doing this right here, 4 is equal to 2, 3, x over y is equal to what? Two-thirds, right? We take the x component, divide by the y component. So then what is y over x?
3 over 2.
Very good, sir. Very good. Okay. Now, notice that 2/3 is approximately 0.6666666 forever. So it's just repeating. I could have stopped it over here. Okay. And that 3/2 is 1.5. Okay. Remember that. Let's pick another point on the line. How about this one, negative 40, negative 60? What is x over y?
Negative 40 over negative 60.
Very good. What does this reduce to?
2/3.
Aha, the negatives cancel, these cancel, so it's really 4 over 6, which reduces to, as this young man said, 2/3. Those are the same. Is this a trend? Let's see if now when we do y over x, do we see some, it would be quite interesting if y over x ends up reducing to 1.5. Let's see. Let's do y over x. What number should I put in the ratio? What goes on top, what goes on bottom?
Negative.
Very good. What does this reduce to?
3/2.
6 over 4, same thing as 3 over 2. Oh my, look. So this is what the book and I are trying to show you, is that even the ancient mathematicians of antiquity, they discovered this trend that there's a ratio between x over y and y over x on any point on the line. That ratio is always the same no matter what point on the line that you pick. Okay, this is what is going to give birth to this subject, trigonometry. This insight, this mathematical insight into these ratios. Okay, so that means this is starting to get exciting, because very soon we are going to define trigonometric functions. You guys excited yet? Thank you, evaporative cooling. I feel a lot better. I don't know what I would have done without this thing. It really saved me today. Consider this situation. So let's have some x1. It corresponds to a y1. This is a line. Let's have some x2. These are arbitrary points. It corresponds to some y2. Okay? And this goes off forever. This is my P2. This is my P1. Let's call this R1 and R2. And yes, it kind of could stand for radius or length. Notice that these triangles we can form here are similar triangles. That was a little tiny piece of chalk for this. You guys see that? Similar triangles. So the ancient mathematicians found that, and by ancient I mean like thousands of years ago, they found that x over y and y over x and x over r and r over x and y over r and r over y. See what I'm doing there? They found that all of these ratios are constant no matter what points you pick on the line. And now we get to define our trigonometric functions. Sine of some angle theta. This is our angle theta. Cosine of our angle theta. Tangent of our angle theta. I'll put 3 lines. The 2 lines means equal. 3 lines means it's defined as. That means that they're equal. But it's a definition also. That way we don't have to write out definition. We can write 3 lines. So it is an equation as well. This, whatever I write on this side, is equal to that. But it's also a new definition. It's a way of saying this is a definition. Okay. Sine of theta is going to be this guy right here. Y over R. Cosine of theta is going to be this guy, X over R. And tangent of theta is going to be this guy, Y over X. Who here has had some trigonometry before and knows has seen sine, cosine, and tangent? Everybody? So what was the mnemonic you used to memorize sine, cosine, tangent? SOHCAHTOA. Yeah, a lot of people remember SOHCAHTOA. What does a SOHCAHTOA mean?
Sine equals.
So.
Opposite or hypotenuse. Adjacent over hypotenuse and
Cosine. Opposite over. Opposite over.
opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Opposite over. Op
Yeah. So notice y is this length right here. This is your y1. This is your y2. So in general, the vertical component is y. And same thing for the horizontal component is x. So sine of theta is opposite y over hypotenuse r. You see that? So it's sine is opposite of the angle theta. Opposite of the angle theta is the y over the hypotenuse. And here the hypotenuse is r. I could have called it h, but we're calling it r. Potato, patata, tomato, tomato, it don't matter. I could have called it q. Doesn't matter. The book calls it r, so I'm calling it r so that you guys don't get confused. I try to prevent confusion. But really, this is SOHCAHTOA right here. So you guys have seen this stuff before, huh? Well, get ready to really understand it this time. Because before, you were just kind of going through the motions and not really understanding why what you were doing was even significant and what it was even talking about. And I'm going to show you and justify everything to you, as we've done so far. However, sine, cosine, and tangent, this doesn't require any justification because they're just definitions. They're just definitions. So they don't require justification. They just are defined to be these ratios. So we don't have to justify anything. I'm not making a statement about them. I'm just saying, here's this thing called sine of theta. Here's a rule of assigning to this angle a ratio, and assigning to this angle another ratio, and assigning to this angle another ratio. Now, what about the rest of these guys here? Who knows what they might be? Notice that this is the reciprocal of that, right? So this is going to be the reciprocal of sine. Cosecant of theta is equal to r over y. It is the cosecant of theta is the same thing as 1 over sine of theta. That's why they reciprocate. That's why what's in the numerator goes down into the denominator. And also, secant of theta is equal to r over x, which secant of theta is just 1 over cosine of theta. And you guessed it, cotangent theta is x over y instead of y over x. So over here we got cotangent of theta is equal to x over y. Those knock out the rest of the possible ratios. So in terms of history, so human beings didn't have trigonometry come out of the sky to them. They had to discover it through reasoning using their brains. What they did was they looked at lines, noticed that points on these lines, their x over y and their y over x always was the same no matter what point we chose. Then they found that their y over r and their x over r and their r over x and y over x was also preserved. And so they invented definitions for these ratios. And that leads to some very interesting mathematics. Now, if you have right here, this is R, it has an associated X, and it has an associated Y. I can pull this triangle out. Forgot to say this was theta. Here's theta. I could create a right triangle out of it, like so, right? So I can determine value of r using the Pythagorean theorem. R squared is equal to x squared plus y squared. This implies the value of r, the magnitude of the length is this. So we typically talk about this situation right here. I'm redrawing the same thing 3 times as being some p of xy, where it has an associated r, an associated x, and an associated y. And that p of xy is just the point at right here in 2-dimensional Euclidean space, which is just flat space. Remember the other day we talked about curved geometries? We just doing flat stuff. The intuitive, but I would say not as interesting, but it still is very interesting. Don't get me wrong. I just like the counterintuitive stuff because that's just like new to me, and it's new to all humans. I don't have an intuition for the curved stuff as much. Okay, so now let's talk about a given situation. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This is p of 5, 5. Here's some angle theta. Find all the trig functions. What is sine of theta? What is cosine of theta? What is tangent of theta? What is cotangent theta? What is secant of theta? What is cosecant of theta? So to do this, we first must determine what the r is, right? Because, for instance, the first one, sine of theta, is y over r. So sine is opposite over hypotenuse. If this is our r, this is our y, this is our x. So opposite is y over hypotenuse r. We already know what the y is. What is it? So now we just need to find the r using the Pythagorean theorem. Okay? And we use this equation right here. This is the Pythagorean theorem. So r is going to be equal to the square root of 5 squared plus, you guessed it, another 5 squared. This is the square root of 25 plus 25. This is the square root of 50. By the fundamental theorem of arithmetic, this breaks down to 5 times 10. And that breaks down to 5 squared times 2. And distributing the radical to both pieces, we get square root of 5 squared times square root of 2. The square root of anything squared undoes the squared. So this reduces to 5 root 2, which is our r. So sine becomes y, which you guys told me is 5, divided by r, which we have calculated to be 5 root 2. And now we just simplify. The 5's cancel. And then what do we do to the denominator? Starts with a r.
Reverse?
Do what?
Reverses?
Yeah, kind of. We typically call it rationalizing the denominator. There is a reversal going on. We multiply the top and bottom by a fancy number 1. Anything divided by itself is the number 1, right? So this is really number 1. 1 times anything is itself. So I'm not changing anything when I multiply top and bottom by root 2 over 2. By root 2 over root 2. But notice when I do this, the top becomes a root 2. The bottom becomes a root 2 times a root 2, which is a root 2 quantity squared. Every time you square a radical, what happens to the radical?
Cancels.
Yes. So what's left is what's on the inside. Yes. So then this becomes root 2 over 2. There you go. That is what sine of theta is. root 2 over 2. Now we got to find cosine, tangent, cotangent, secant, cosecant. Let's go. What is cosine? It's x over r, right? So, sorry, that part. What is our x? What is our r? Very good. So we just cancel again, 5s. Notice this is the same thing as above, interestingly enough. So we get root 2 over 2 again. This is our cosine of theta. Interestingly enough. Wow, not always are sine and cosine the same. This must be some special situation here. Now, let's do tangent. Tangent of theta is y over x. What is my y? What is my x? What is the ratio of 5 divided by itself? So tangent of theta is a 1. So we've checked these guys off the list. These guys are really easy once you've checked their counterparts off of the list. These are just reciprocals. So look, cotangent, remember, is 1 over tangent of theta. Secant is really 1 over cosine of theta. And cosecant is really 1 over sine of theta. So all we got to do is take the reciprocal of 1. 1 reciprocated is 1 over 1, which is 1 again. So cotangent of theta is 1. What about secant? Secant of theta, what was my cosine? If I want to know what secant is, I just got to get cosine. Flip them. Flip them. So I get 2 over root 2. And as you've been trained, you should get this feeling like, get this weird feeling like, oh no, there's a radical in the denominator. I want to get rid of that. So we rationalize the denominator by doing what? Fancy number 1. Very good. What is the fancy number 1?
Square root of 2 over square root of 2.
Yes. If this was a square root of 47, I'd multiply top and bottom by square root of 47 divided by square root of 47. Okay. So then this ends up becoming 2 root 2 all over 2. Cancel out the 2's. Just a root 2 as you said. And this is our secant of theta. Last but not least, what is the cosecant of theta? What is our sine? Root 2 over 2. Flip it. We notice that's the same thing over here. So it's going to result in a root 2 again. So we found them. Not always will they have the same values. You will see as we progress in this class that this was a very special situation, that the sine and the cosine had the same values. This does not always happen. Matter of fact, the majority of the time it does not happen. Okay? Can you guess the angle? Let me redraw what we had. Can you guess at what angle this was in? And if you've had this class before, it'll probably make it easier for you to really determine what angle that was in. Here was the situation I've deleted. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This is at 5, 5. Who can guess what this angle is? I don't want a calculation. I mean, this is the one time I don't really want calculations. I just want you to just tell me, eyeball it. Give me a degree, and then give me a reason for why you believe it's that.
45 degrees.
Oh! Who here agrees? Who here disagrees? Nobody disagrees. Why do you think it's 45? I'm not going to say it's right or not yet.
Because, well, you said an eyeball, so it's right dead center at 45 degrees. And also, if it's 2 root 2, that means that it's 45 degrees. We learned it on like our trigonometry circle.
Those are all very good reasons. Very good reasons. Another thing that you could have cited, another concept that you could have referenced was something we talked about last class period. Notice if I turn this into a triangle like this, this is the triangle we would get. It'd be a right triangle. Here's our theta. But notice if this is 5 and this is 5, what kind of a triangle is that?
Isosceles.
An isosceles triangle. What was the characterization of the isosceles' internal angles?
2 same lengths and 1 not the same.
Correct. But what does that imply about the angles?
They're equivalent. They're equal to each other.
2 of them are equivalent and they're equal to each other, and one of them has to be 90. So we have 180 degrees is equal to same thing plus 90. What must these things be if they're the same thing?
45.
Aha! That's what I wanted to hear. Yes, very good. So this is another way of seeing it, is that situation forms an isosceles triangle. The angles must be the same, the ones that are not the right angle, and that implies that it have to be 45. All of those ways of determining what theta is a very good way. Now, more. We want more. We want more math. Given something like this, before I continue, and you guys may already know this, but I'm going to have to talk about it again. Whenever you get the Cartesian coordinate system, you create 4 quadrants, right? Here's a Cartesian coordinate system. It creates 4 quadrants, right? The way in math we denote the quadrants are, this is quadrant 1, this is quadrant 2, this is quadrant 3, this is quadrant 4. Okay. So then now I can talk about this here. Let's say this is the line y of x is equal to negative 12 over 5x. Here's your task. Task A. The terminal side in quadrant 2 is coincident with y equals negative 12 over 5x. Okay. Given some point P of x is a point on the terminal side of angle theta in standard position, find the sine of theta and cosine of theta. For quadrant 2. So meaning, here's our theta here. What is the sine and cosine values for quadrant 2 over here? Meaning, here's our initial leg. Here's our terminal leg. Well, the way you do this is the way we've been doing it. Sine of theta is y over r. Cosine of theta is x over r. Well, what is r? Well, you need the x and y to determine r, correct? So what the problem is really kind of making you do is what we did earlier with that like -40, -60 stuff, is it's imploring you to use the equation of a line, input a negative x so that your output will lie in the second quadrant. Somebody give me a negative x value. And pick a really nice one, like -5. I'll tell you why I'm picking that. Then y of x equaling -12 over 5x. That implies y of -5 will equal -12 over 5 times the -5. Notice that not only do the negatives cancel, so do the 5s. So we get a really nice whole number, 12. We'll come back here. That means this over here is at 12 on the y-axis right here. This point right here is -5, 12 on this line. Making sense? Very good. Because now that we found that, we can find r. Because now we know an x and a y, don't we? And how do we find r? The what theorem? Yes, the Pythagorean theorem. R is square root of x squared plus y squared. So let's find r. What is r? Square root of what squared?
-5.
There we go. Square root of -5 squared plus 12 squared. This is equal to the square root of 25 plus 144. Yes, it becomes 169, and the square root of 169 is 13. So this implies r is equal to 13. We have everything we need to find sine and cosine. What is sine? What is sine?
12, 18.
12, which is the y component, over 13, which is the hypotenuse. Done. And we satisfied what the problem wanted. We found it in the second quadrant. We found what this angle, where is it in the second quadrant? Now, what is the cosine in the second quadrant?
13 over 12. No, wait, cosine is 12 over 12 over, no, 5 over, -5 over 13.
Aha! Because it's x over y, you're eventually going to get one of the numbers. There's only 3 numbers. There's a -5, a 12, and a 13 to work with. So -5 here is the x. So that's why it goes in the numerator. And the denominator is that 13. Very good. Very good. Done. Done with that, not done with everything. It just keeps getting better and better, doesn't it? You guys look like you love math. Who in here is a math major? Math education major? Who here wants to get their PhD in mathematics and do research in number theory? Not yet. I'm going to make you want to do that. I'm definitely going to lobby for it, you know. I'm going to do my best to try and make you want to become mathematicians. And that's what you want. You want your teacher to do that. That means they're really going to strive to make you learn it as deeply as possible. And if I'm ever giving you extra information that won't be on the test, I let you know. Say, here, this is for your enjoyment. If you want to be enjoyed by it. If you want to enjoy it. If you don't want to enjoy it, then it is what it is. I tried. I gave my best shot. I can sleep good at night knowing that I put in a very tremendous effort. Okay. Now, what if we wanted to find sine and cosine in quadrant 4? So let's do this whole thing again for quadrant 4. Give me an input for the y of x is equal to negative 12 over 5x. That will land me in a spot on the line. And pick a good number. A good number that would cancel this 5 out here.
Positive 5.
Aha. Positive 5, because that positive 5 is here, meaning the output will be over here. So y of positive 5 is equal to negative 12 over 5 times positive 5. Y's cancel and I get a negative 12 here. Makes sense? That's a good sign because it better be negative if it's down there. The negative 12 better be there. Okay. So now we have a point. It is 5 comma negative 12. What's sine and cosine now? Better yet, let me ask you, does the calculation for r change? The x is now positive 5, but okay. And the 12 is now a negative 12, but I mean, okay. You're going to square it so the negative goes away anyways. So your result is still r is equal to 13, whether it's here or there. So what is our y over r? And what is our x over r?
Negative 12 over 13.
Mm-hmm. And what is our x over r?
5 over 13.
Very good. Very good. Simple as that. Okay. Moving on to different kinds of problems. You kind of get the point of this now. One of the main things is know that I can plug in for any x I want. I can get an output y. That's on the line. That's one of the key components to understanding this. After that, sine and cosine and tangent and secant and cosecant, they're all just definitions that you can, I guess, memorize using SOHCAHTOA. So let's play another game here. Let's play a math game. Let's take notice. If this is quadrant 1, this is quadrant 2, this is quadrant 3, this is quadrant 4. I'll give you the first one for free. Sine of theta in quadrant 1 is positive, and cosine of theta in quadrant 1 is also positive. Right? Because every time you think of sine of theta, I want you to think of y or vertical. And every time you think of cosine of theta, I want you to think x or horizontal. If I'm in quadrant 1, at any point in quadrant 1, my horizontal values are positive because this is to the right of the origin. And my vertical values are positive because this is above the origin. So sine and cosine are mutually positive in quadrant 1. What about quadrant 2?
Sine is positive and cosine is negative.
Oh. Why are you saying cosine is negative?
Because if cosine is x and it's going to the left of the origin, so, I mean, yes, right. So it would be negative.
Absolutely correct. Absolutely correct. What about quadrant 3? Oh, hey, look, we have them right here too. Look, 1, 2, 3, 4. It says it right here. Cheat sheet on the exam. You can just look at that if you forget. What about quadrant 3?
All of them are negative. Cosine and
All of them are negative, sine and cosine. Why?
you're still going to the left for the x, so that's negative, and then you're going downwards from the origin now on the y, so that would be negative.
Correct. And you might as well just top it off and tell me what 4 is.
Sine is positive for the 4 and cosine is negative.
Are you sure?
Yes.
Sine is positive?
Yes.
Sine, the vertical component, is positive down here?
Yeah. Because it's going to the right.
Vertical. Sine stands for
Oh, sorry.
vertical. Uh-huh.
It's the other way. That's right. Sine is negative, cosine is positive.
Aha. Sine of theta is negative because sine of theta represents y, or the vertical. And cosine ends up being positive because cosine represents the x, or the horizontal. Now, let's play a game since you know this right here. What quadrant does the terminal leg land in if cosine of theta is less than 0 and cotangent theta is greater than 0? You got a 25% chance if you guess randomly. But let's have an educated guess. And matter of fact, let's just not guess at all. How about that? Let's start to think and apply some reasoning. Which quadrant is it going to be in?
Both of them or just one? Like, is cosine and cotangent both in one quadrant?
Yes. So the angle is both in one quadrant. So that's a great question. That's a good question. So I'm not saying this is the quadrant it lands in, but take a look. Here's our theta, right? Here's our terminal leg. This terminal leg has to be in one of the quadrants. In this case, it's quadrant 2. So at this location, we can define all 6 trig functions. So this is saying you don't know the quadrant, but you know what the signs of the trig functions are in this unknown quadrant. Determine the quadrant. So if cosine is negative, we can cut our choices in half. Notice that over here, cosine is positive. So there's no way it could be in the first quadrant, right?
It could be on the second and the third.
Aha, and right, by the same token, if cosine is negative, there's no way it could be in the fourth quadrant. So it's like on Who Wants to Be a Millionaire? Now you have 50-50. Who wants to be a trigonometrician?
It's the third quadrant.
It's the third quadrant. I want to hear a justification before an answer.
Because cotangent is x over y, and whenever you have 2 negatives, that equals positive, and that's why it's in the third quadrant. And also cosine is negative, so then cosine is also negative and belongs to the third quadrant.
So you're saying third quadrant.
Yes.
Your team third quadrant. Who agrees? We have like everybody agreeing. Who disagrees? Okay, let's hear that description one more time, a little slower. Why do you think it's third quadrant?
Well, you already cut our options in half.
Half, so it's either this or that.
Cosine is negative, so it belongs on the left side of the y-axis. So and we got that out of the way, so it can either be the second or third quadrant. And cotangent is x over y, and whenever you have two negatives, that equals a positive. And whenever it's not the second quadrant because sine is positive, and if you get a positive with a negative, that's always going to equal a negative. It needs to be greater than 0. So the third quadrant is where it belongs because both sine and cosine are negative. So then that makes it a positive.
Yes. Very good description. A very good justification. Does that make sense, everybody? We'll do more of these. This is just something you're going to get better at with repetition. Okay? The same kind of questions here. I'm just going to give you another situation. I'm just inventing here. How about cosecant of theta is less than 0 and secant of theta less than 0? So I think what's best in trying to solve problems is to not just boom have the answer in your head, because it just doesn't work like that. Do you just like go into your car from here and boom you appear in Dallas? No, because we have not figured out how to create exotic matter which pries open Einstein-Rosen bridges, forming wormholes. Remember we guys talked about wormholes? Yeah, we haven't figured out how to do that yet. So it doesn't work like that. You have to go through a pathway to reach Dallas, for instance, from here. Let's talk about how we do that in our head for these problems. Well, the best thing is to look at one of them, whichever one you want, and to think about it first, independent of the other one. Okay? So let's just look at this one first, without thinking of that one yet. Cosecant of theta. What does that equal to?
Sine.
1 over sine of theta, right? So this is the same thing as that 1 over sine of theta is negative. Okay? Right off the bat, I can cut our possibilities in half. Which quadrants are no longer valid? 1 and 2, because 1 and 2 have positive sign. We only have to restrict ourselves to the negative sign, okay? And sine represents vertical. So positive vertical is above this horizontal, and negative vertical is below the horizontal. So because we need negative verticals, these are out of the picture, okay? If you guys pay really close attention, this will make sense. Okay, then now that we figured that, this piece of information allowed us to cancel out those quadrants. What does this piece of information tell us? What is secant? Very good. And that's less than 0. So out of 3 and 4, why is it the third quadrant?
Because both sine and cosine are negative at the third quadrant.
Correct. At this, yes. At this point, both the quadrants have negative sign. So you only need to find the quadrant that has negative cosine. Because here, this quadrant has positive cosine. So this piece of information right here, which means we need to have negative cosine, effectively removes this as a possibility, leaving only one possibility, quadrant 3. Okay. To finish off, let's talk about quadrantal, or what do they call it? Quadrantal angles. That's right, quadrantal angles. I always almost say quadrilateral angles, but that doesn't make sense. Quadrantal. The quadrantal angles are the ones that occur on the axes. 0 degrees, 90 degrees, 80 degrees, 270 degrees, 360 degrees, and so on and so forth. Why do we care about these angles? Well, some funny business occurs at these angles. Let's analyze angles 0 and 90 for their sine and cosine. What is the sine of 0 degrees? And what is the cosine of 0 degrees? I erased it, but sine parameterizes what? The vertical or the horizontal component?
Sine is vertical.
Sine is vertical. How much vertical do we have here?
None.
No vertical. It's completely horizontal. So if it has no vertical, it's equivalent to 0. Now in turn, what is the cosine of 0?
360. No, it's 0.
Cosine of 0 and cosine of 360 will provide the same value. How much horizontal do we have here? You know what? I'm not giving you the information you need here because, yeah, that's kind of my fault. How much horizontal do we have here?
1.
1, yeah. So here we go here. Now let's talk about sine of 90. And cosine of 90. Here. How much vertical do I have?
1.
Aha! And again, how much horizontal do I have?
0.
None. Okay. To finalize this discussion, the last thing is, well, that's sine and cosine, but what about tangent? What is the tangent of 0 degrees? And what is the tangent of 90 degrees? Recall, tangent is y over x. Recall that if sine of theta parameterizes the y coordinate in the projection of a circle, that means this is sine of theta divided by cosine of theta. So that means tangent of 0 is sine of 0 over cosine of 0. Wait. Sine of 0 over cosine of 0. Pointed at the wrong thing there. Sine of 0, cosine of 0. So what is 0 divided by 1?
0.
0. Well, nothing weird going on yet. But what about the tangent of 90 degrees? Again. So 90 degrees, so sine of 90 is 1. Cosine of 90 is 0. What is 1 over 0? Undefined. Have I proven in this class why you can't divide by 0 yet?
Because it's not valid.
No, you could prove it. We're out of time, but in next class period, I will prove why you can't divide by 0. Like, justify it fully for you. Yeah, it's going to be cool. It's going to be, as you younger generation folks say, it's going to be lit.